Hey guys, so I was in a hurry trying to finish this up and I didn't get done. So I'm going to go ahead and go back to where I was. We were looking at this last function. If we know that f of 1 equals 7, so this is our x and this is our y. So 1 is 7. 2, f of 2 equals 7, so if I plug in a 2 for x, then that also gives me 7. F of n doesn't tell me what 3 is, but if this is f of 3, so if I plug that in, f of 3 is equal to f of n minus 1, so that would be f of 3 minus 1 is 2, f of 2, plus n minus 2, so 3 minus 2 is actually f of 1. So I'm going to add these two behind. 7 plus 7 gives me 14. Then to find 4, you actually, for f of 4, you are going to add f of 3 plus f of 2. So that is 7 plus 14, so 21. And then f of 5, you do the same thing. You do f of 4 plus f of 3. So 5, I'm going to squeeze it in there, would be, what is that, 35? You are adding the two previous. That is not, we're not going up by the, we can tell immediately we're not going up by the same, we're not multiplying by the same number, so this is a neither. And then here it tells us that f of 1, so if this is n and this is f of n, or x and f of x, it doesn't matter which function you're using, 1 is equal to 1. If I plug in 2, f of 2 is going to be equal to 2/3 of f of n minus 1. So if I plug that in, f of 2 minus 1, well, f of 2 is equal to 2/3. What is f of 1? Well, it'll just be 2/3. If I plug in 3, my f of n is 2/3 times the previous number. So 2/3 times the previous number is going to give me 4/9, because 2/3 times 2/3 is 2 times 2, 4, 3 times 3, 9. If I plug in 4, that means I take the previous number of 4/9, multiply by 2/3, then that gives me 8/27. So if we are multiplying to get to the next number, then that is going to be exponential. You can make a table, you can make a graph, you can discuss that multiplying means that it is geometric, which goes hand in hand with exponential. This would be recursive, right? Because it's got the f of n and the f of n minus 1. I've got a few more problems. I've copied these, or I posted these for you. I didn't copy them. I posted these for you if you're looking for a little more practice. It says comparing rates and change in both linear and exponential situations. Identify whether the situation A has a greater rate of change than B. Which one is bigger? So you can see that these are A is on this left-hand side, and this is B. If I have to find my rate of change, then I'm going to see negative 10 goes plus 1, negative 9 to negative 8 is plus 1, and then how does negative 48 turn into negative 43? It's getting larger, and then I can see this should be plus 5. If we see our pattern, we're going up by 5. So my rate here is 5, my rise over my run, 5/1. So as a slope, we would just represent that as 5 over 1. The hardest part for the graphs is finding your perfect points. See how this point right down here, that just looks like it's crossing perfectly. Here is a perfect point, and here is a perfect point. So if we find our slope on this graph, we're finding our rise over our run, which we've talked about several times, and it's going up 1, 2, 3, 4, 5, 6 over 1. So that means our graph actually has a greater rate of change. The way it actually showed the greater rate of change here, if we're looking at how quickly we move, if we find the end of our graph over here, it takes us 1, 2, 3, we're past 3 in order to hit, the graph is the same size, but if we look at how long it takes us to hit the top of the graph here, we're actually looking at just 1, a little bit past 1. So actually in this case B still has the greater rate of change. It's moving faster. If you wanted to look at it down here, we're both of these are starting at 1, and it's really kind of hard to see that. The graphs are kind of hard to see. This is your X and Y axis. If I were to draw those in, this is my bad Y axis, and this is my bad X axis. This is my bad X axis, and this is my bad, really bad Y axis. But we're starting here. Both of them are starting at that 0, 1. Here, I'm going up 1, 2, 3 over 2, up 1, 2, 3 over 1, 2, 3, 4 over 1. So that's moving faster. Here it's moving 2, 3 over 2, and then up 1, 2, 3 over 1, and each time we're getting closer and closer to the top of that graph. It's still taking us 1, 2, 3 spaces to get over there, but here we're moving up much faster. 1, 2, 3 over 1. Actually, it would be 1, 2, 3, 4 over to that 1. So B's moving a little faster. If Lee has $25 withheld each week from his salary to pay for his subway pass, withheld means negative 25, negative 25. Jesse owes his brother $50. He has promised to pay half of what he owes each week until the debt is paid off. Half, just one time, is going to be 25. And then twice, if you think about it, if he pays $25, that's minus 25. At 1, it's 25. At 2, it's 50. Well, we'd already pay that off. Over here, we're saying the first week we're going to pay from 50 to 25. The second week we're only going to take it down to $12.50. So A is going to be faster. Got a couple more here. We are going, this one's interesting. My X doesn't go up by 1. My X is going up by 4. Plus 4, plus 4, plus 4. And here we are going up plus 2, plus 2, plus 2. So if I rise over our run, we are actually going up 2 over 4, or 1/2. For slope, or rate of change will be 1/2. The number of rhombi in each shape. Well, this has 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Why did I write a 1 there? I should have written a 3. So we're going up to, the next one would be 9 if we add 2. Sorry, Miss Baker is tired. It's the end of the day. So this would be 9. So which is bigger? Is 1/2 bigger or is +2 bigger? This rate is going to be larger. Here, our rate that we're moving up, we start at 2 and we're multiplying by 5. This is multiply by 5. In the children's book, The Magic Pot, every time you put one object into the pot, 2 of the same objects come out. Imagine that you have 5 magic pots. Well, 5 magic pots is where we're starting this time, and 2 is we're multiplying by 2. So once again, this is the starting point. 5 is the starting point now. 2 is my rate, my multiply by 2. So multiplying by 5 is going to be a larger rate. The only thing that we have left to discuss, and I've just got a few minutes, are those graphic organizers that you all have on your page. The graphic organizer is the one that has linear functions. Things that we need to remember about linear functions. Their equation, they are going to be in y equals mx plus b, where m is your slope or rate of change and b is your y-intercept. I'm going to write that in there too. Rate of change and starting point. Our tables are always going to go up the same. So if we have x and f of x or n and f of n, so if I have 0, 1, 1, 3, 2, 5, 3, 7, you're always going to see this as +1, +1, +1. As long as they're going up the same rate on both sides, +2, +2, +2, then that's going to be linear. Our graphs, I'm sorry, I know this is a mess. Our graphs are just going to make a line. All of them, they could be a positive line, a negative line. They can even be a horizontal line, but those are lines. Context, if you want to talk about the context, we're talking about anything that goes up at a constant rate. Constant rate. It can go up or down at a constant rate. Okay. The definition, I'm going to skip that. That's just words, and Miss Baker's not good with words. I'm going to stick with this stuff right here. We can say that as a sequence, this is arithmetic. Arithmetic, right? As a sequence, it's arithmetic. Our next page, we want to say something about exponential equations. They are in the form of y equals a times b to the x. We've always got an exponent. This is still our starting point. And b is still what we multiply by. Each time. Our tables and our graphs are going to explode. Our graphs are either going to start off low and then jump up real high, or they're going to start off real high, just like the water in the pool, and then quickly go down. And then it levels out. And our context is anything that is growing.